morning. I'm Mingxi Zhao. I'm a first-year master student in MSBIC program at Carnegie Mellon University. Today, I'm going to give a presentation about a special machine learning task. It is the Intrusion Detection Learning on the KDD CUP 1999 dataset using RHadoop. First, I will talk about this task. In this task, we are going to detect abnormal network connection. It may be a network intrusion. This is very important to protect a computer network from unauthorized user. The dataset we use, the training data is the KDD CUP data using the 10%. It is about 494 and 21 records. And the testing data, I used the KDD CUP test data. It is about 311,029 records. Each line of the dataset represents a network connection record. Each record owns 41 features and one label, indicating whether the connection is normal or attacked. The attack will along with a specific attack type. The attacking type will mainly fall into four main categories. They are the DOS, R2L, U2R, and probing. Or the specific label will be one of the four main attack categories. Before training and testing the data, I do some pre-processing. First, I remove the redundant data. Because there is huge amount of same attacks in the dataset. For example, the line 460 and 1,798 and the line 4790845 in the training set is exactly the same. So the algorithm will be biased towards frequent records and prevent from detecting infrequent attacks such as U2R and R2L. This is why we should remove the redundant data. After remove the redundant data, the distinct records in the training data is 145,586, and the distinct records in the testing data is 77,291. And I do some feature engineering. For example, I use the attack types, not original categorical label, because the training datasets contain a total 24 training attack types, while the test dataset contains additional 14 types. So I will classify the overall 38 specific types into the 4 categories. Otherwise, it will result in incompatible in the training data and the testing data. Another feature engineering I do is the normalization. Normalization means adjusting values measured in different scales to a notionally common scales. For example, I turn the string value to int value, so it can be calculate numerically. For example, the TCP I assigned 0 to the TCP label, and I assigned 1 to the UDP attributes. I mainly use free learning algorithms. They are decision trees, naive Bayes, random forest. First, I use the naive Bayes because it is the simplest algorithm that I can implement, and it has many advantages. For example, it has a very high accuracy. Let's see the confusion matrix. I can see the precision can reach 91%. I think it's because I do the feature engineering and the pre-processing. Naive Bayes have a lot of advantages. For example, it can reduce the dimensionality curves, and it's simple and easy to implement, and it is fast learning. But there are some disadvantages. For example, it can perform poorly if the independence assumptions do not hold, and it can overfit to the training data. So I try another algorithm. It is the decision tree. The decision tree can also handle the noisy training data. So the precision is over 93%. But the decision tree has some problems. For example, it will has the high variance and the overfitting problems when the tree grows deeper. So my solution is to use another approach. It is the random forest. In the random forest, we can achieve a precision about 92%. But random forests also have some problems. The complexity is very high if we use all the features, so the algorithm will run out of memory. My solution is to do some dimensional reduction. I remove the near zero variance in features. Datasets sometimes will contain features that are constant or almost constant. This kind of feature is not only non-informative, but also will influence the efficiency of the algorithm. So we better remove them. For example, the wrong fragment and the urgent attribute of the original dataset is the near zero variance features, so I remove them. I also do some cross-validation. For example, use the k-folds cross-validation, and the result is the precision increased to 96% for naive Bayes compared to the baseline of 91%. And in the future, I think I can do a better future engineering. For example, I will give larger weights to important features. This will greatly improve the performance of the algorithm. So that's basically what I done about this project. Thank you.